guess you're finished the activity now. You can tell me everything we need in smart grids. Okay, I have 15 or so more slides regarding the details of smart grids. I want to get your what you came up with first. So what is the, let me start with the first one. What are the problems that smart grids are trying to solve? So matching the demand and the supply based on how people are using electricity throughout and during the day. What are other problems that smart grids are trying to solve? Okay, those are the main ones. What are, how are they trying to solve them? There's a short answer for this.
Smart grid.
By doing things smartly, basically. I guess the detailed answer for that is with the components that are needed to achieve it. So what are the components that you need? Yeah. Networks. So communication networks, I'm guessing. So you need feedback. You need information of what people are using as soon as you can get it. So within like minutes or within the same hour, in order to figure out where the demands are and only provide power to meet those demands, rather than over provision and have wastes of in terms of heat dissipation and conversions, then sending that electricity which is not going to be used. What other components are needed? What components are needed in your household? How do you get that data? Sensors. So you need the particular components, we'll mention them. There are, they have to be put in the household and some of them in the different, on the way in the distribution centers in order to figure out where faults are and what the demands are. Okay, any more components? Okay, yeah. It has to go back to one place. One possibility is towards the middle, so towards the distribution center, which can readjust its strategies and its power transmission depending on where the usage is. And if you think about, let's say, events that are happening, let's say there's the Olympics happening, everyone's going to be watching TV during that time. During that time, you need more power. Yes?
Can it also be sent to the source so they don't have to convert, let's say, fossil fuels into energy yet if it's not needed? Because once it's can you store it? Can you store electricity? Or once it's created, it has to go somewhere? So if it can't be stored, there's no point in it.
Trying to there are going to be losses with it. I think it's hard to store.
Yeah, so if you can't store,
I mean, you have, yeah, with generators.
If you don't have to have a steady flow of the same amount of creating the energy. Right?
Well, in order, if you're using, for example, in generators, you don't use huge batteries to store things. That's the thing. But when you think of, in the future, if you think of electric vehicles as part of the power grid, and you start having millions or billions of vehicles, electric vehicles could be your batteries that are moving. They can be transporting electricity from on the way, right? That's another way of looking at things. And one of the most interesting comments in the video we saw was there are going to be things that we can't even imagine now with smart grids. So try not to oversell it. Start with what you can implement now, start implementing it, and then the applications are going to be different. There are new ways we're going to be perceiving information and new ways we're going to be using the data that we're gathering from our sensors in order to have smarter applications and improved performance. Okay, So let's go back to defining smart grids in a better way. The drivers of smart grids, you start with cheap and fossil energy, which is coming to an end. Previously, when we started using fossil fuels, we thought they were abundant. We thought they were going to go forever. Now there are different stats and predictions that by 2050, we're not going to have any more fuel. So we need to have different means, fuel or gas or different elements. Now, one of the other things with this is the fact that because the supply is lower or getting lower, the prices have gone up. So it's costing far more to use what we had before. So price increases have led to basically an unsustainable solution. Okay, so if things are expensive, then I can't guarantee that in 5 years I'll be making this much money, I'll be selling my devices for this much price because I don't know what the fuel price is going to be. So I need a better solution. So another element is competition. So yesterday we were talking in cloud computing how competition would lower prices. Again, having multiple utility companies, having a more liberal market would enforce competition, would reduce corruption, would make people do things more efficiently, and would lower prices for the users, right? So competition and innovation lower prices. Currently, what the systems that we have, a lot of the systems that we have in North America are, in power grids, are 40 years old. And there hasn't been investment in infrastructure to improving these things because things have been working. And we don't have a liberal market, so you have one source, so they don't have to actually change things. Things are working, they don't have to change things. And even if things are lossy or not optimal, they're not obliged to change things. Unless you have other people who are coming in, other utility companies, and they are allowed to produce, and they can provide cheaper options. And what that is going to do is your original utility companies have to do things better, right? Have to change their ways, have to put smarter devices in their systems and do things more efficiently. Energy security and availability. So we need to ensure that energy is going to be available and having a certain reliability and quality. We have to ensure, because our businesses depend on these. If you check for money losses due to power outages, just in like North America and every year, they're in billions of dollars. Small power outages cause lots of money losses. It's just because of how much we rely on electricity. So we need to ensure the capacity that it's going to meet the demand, and at the same time we need to minimize outages because outages are going to cost a lot of money. Now, other elements are environmental factors. So so power generation creates most of the CO2 emissions, and we need to reduce that. And one of the things that this has been causing is climate change with global warming. And a good example is how warm the weather has been this past winter in Toronto. Surprisingly. Okay, so definition of smart grid. Smart grid is a device that integrates conventional and leading edge power system devices, power electronic switches and converters, sensing and monitoring technologies for your data, information technologies and communications in order for your data to be transferred. And through this technology and protection strategies, it solves the generation to load ratio problem, which is similar to that in cloud computing. So another way of looking at this is the peak to average ratio problem. That's in another word. So that means you're generating, but you're using less. Your load is actually less. And you need to minimize the gap between these things. You shouldn't generate far more than your load. This is similar to the graphs that we saw yesterday with cloud computing, where your capacity, is far more than your typical usage. And we need to figure out a way to get that information from your system, from your power system, in order not to generate more than what the actual load is. So this is the main problem in smart grids. So in addition, you have minimizing environmental effects due to the CO2 emissions, and enabling interactions between customers in real time. So you need your, you don't want to go to the end, at the end of the month to figure out how much you've spent or where you've spent that energy. You need to do it in real time. And if you have that in a liberal market where there are different producers and different users of power, imagine that you can get power from different users and one of them is giving it to you cheaply, then you would go to the cheaper option, right? You can do this over time. You can auction power, just like you can do auctions on eBay, for example. Things would look very differently, and resource usage would be far more efficient. And create self-healing and automated solutions. So you don't want someone to call and say there's a power outage, go and try to figure out where it is, and during that time there's losses to businesses. You want automated self-healing solutions. So you have a problem, before the problem happens, you can be able to detect it because of the voltages going too high, for example, and you can solve that problem easily. Hopefully the devices by themselves will be able to solve the problem. Okay, now let's go to the components. One element is a smart meter. This is the device that needs to be plugged in at home. Another one is voltage phasor measurement. This is on the lines in order to figure out where the faults are, or where the faults are could be. The communication mechanism for information transfer, and distribution feeders or the generators. Okay, the distributors or generators. Okay, so now we can look at have a wider view of the network. We can start from here. So the red, that is where we are generating electricity. Okay, so you have your traditional power generators, and you have your newer, more energy efficient power generating systems. So those are the large scale ones. Here, so this is what we're looking forward to. This is what smart grids are all about. Here on the way you have the transmission centers. Okay, the transmission centers with that do convergence from higher voltages to lower voltages, approaching your households or your businesses, and all of those conversions, as we mentioned before, generate a lot of heat, which is considered as a loss in an electric system. One good example is my laptop is heating up. That's not something I intended for. The intent of my laptop is to have a presentation, but the heat is an electric usage or a loss in my electric system that I didn't intend for, but it has to be there. So all of these are going now to the residential areas, and there are sustainable solutions there. Okay, let's go back here. So at the top, now you have controls and sensors. So this row here, you have controls and sensors all throughout your system, starting from your generation systems to your distribution systems to your households, in order to figure out where the faults are, what the demand is in different places, and adjust to it, according to that. Next, you have the integrated communications. So here, you have you have all of this information has to be integrated in order to be able to transfer information back and forth and know what is happening here, and based on that, generate electricity. Now, then you have data integration. So there are elements there where you're forecasting what the usage is going to be like and adjusting to it. You're using historical data, the measurements that you have done before, and you have your real time. So based on your real time, if you need more power, you generate it, you send it, you convert it, you send it, it reaches your household, rather than having huge amounts of energy that's sitting there, that's not used. Other data and application integration. So you have different mechanisms that go on top of this. So on the top layer, you have applications. Now we start talking about smart applications. I mean, if we think about applications, we think computers, we think networks. We don't necessarily think about power grids. But now that you're talking about a data world, when you're getting all this information, your optimization, your system performance is being done by a particular application, and there are various things that you can improve. So there's power management operations in your generator systems. If there is lots of consumption in making these up, I don't know the power systems in the area. If there's huge consumption in the east of Toronto, for example, you might wish to generate that power in Oshawa and send it from there because it might be cheaper, and a power system in Mississauga, for example, is already overloaded. That's one example. So you can optimize which generator you're using in order to have that energy that that you need. Then you have your regional transformation, or the distribution centers also play a part. You can optimize how they're working. And within your own household, you have distribution control centers, and you have your end users have their optimized devices. So you can optimize the usage of different devices in your homes. That's why you hear about smart homes, where your fridge or, I don't know, washing machine or dryer will turn on at night during a time that is cheaper for you, and you don't need to be awake to turn it on manually. So that's when you can have the applications. You can communicate with your electric vehicle to start charging at a particular time, again, for a particular optimization. Okay, so let's talk about the different components now. So you have the smart meters and the home area networks. Here, this is an example. You have the utility energy that's going in. You have the electric meter, and you have a Zigbee. That's a wireless standard. That's the communication mechanism between different devices. So you have smart appliances, home automation system, lighting controls, gas meters, so on and so forth. The task of this smart meter includes the following: recognize the exact electric consumption that you have with the different devices. Relay this information to a central system, so that the central system, which could be the distribution center, for example, would adjust the power generation in order to meet this usage. Enable users to adapt their consumption based on the time of day. So we were mentioning before that if you're using power after midnight, it's cost you cheaper. So you can adjust at how, when your systems are being turned on, especially the ones that you don't need all the time, in order to reduce your time of use pricing. Reduce peak usage periods. The worst part of the power system is peak usage periods, because you're consuming so much energy at that time and releasing so much heat. So by interacting between different people, we want to be able to reduce that. Could interact with smart appliances that can provide improved performance. And here you start having the questions. Now, if every household is plugging in the smart meter, what degree of control can be given to the utility? So are you the one deciding when this device is going to be turned on, or is it a centralized system that is connected to different smart meters in a particular area, and it turns on, you turn on now, you turn on now, you turn on now, and it is optimizing for different smart meters within a particular residential area, let's say. Okay, so that's an important question that we need to think of with the usage of smart meters. Another element is what social or pricing incentives are effective. How can you incentivize people? How can you motivate people in order to act in a way that would be good for them and also good for the society, right? So that's what we're going to be talking about this afternoon. Okay, so now let's go to one of the important technologies in here. It has to do with microgrids. This work is done by a professor in electrical engineering in power systems or energy systems in electrical and computer engineering at U of T, Professor Reza Iravani. So your conventional distribution feeders, which is the ones that provide electricity, have radial topology, have one-way power flow, so it goes in one way, it doesn't come back. You have disconnected and de-energized during faults. So it looks like this. If you look at the arrows go down. Okay? So the red ones, look at the red ones, the power flow is unidirectional. Okay, so this is your radial feeder, this is what it looks like, this is what the topology is, and you have different loads here in different places. The blacks are the loads. And you're generating, you're sending, you're converting, you're sending, and then you're using, but you don't know what is happening here. You don't know what is being used when. You're not getting that information in real time. So this is the existing distribution feeder. Now, the problem here is this is disconnected and de-energized. So you don't know what is happening, and this could be there could be a fault here, and then it's gonna take a lot of time to figure out where the fault is, and that is how things are now. Okay, so microgrids, as I mentioned, this is one of the most important elements of smart grids, most important components. A microgrid is a cluster of distributed generation and distributed storage units that are serviced by a section of a distributed system and can operate. First of all, they can operate in a grid-connected node. They can work in an autonomous mode or an islanded mode, and between having a transition between these two things. Let's go to the picture so that you'll see this more. So here, the one way of looking at this is you have your different ways of generating the energy. You have your different loads, and the key part here is you have distributed storage units. So that's what you're asking about, whether you can have a storage system. So what you're trying to do is you want to send this power, you're trying to store it in different places and use it whenever it's needed. So you need your backup power somewhere nearby so that when you need more energy, it's right close to you. And these sources are close to you, and they could be, for example, at a lower voltage, hopefully. Now, when you think about an intelligent microgrid, this starts incorporating the elements that we're talking about in smart infrastructure. So intelligent or smart is the same thing here. So then you start thinking about sensing and monitoring technologies. So now you know what you need when someone says smart, right, or intelligent. You need the data, so you need sensing and monitoring, and you need ICT, which means the communications. You need bidirectional power flow with main grid. Okay, so if you're generating electricity and you're sending it, and it's more than the demand there, then you need a way to send that electricity back and use it somewhere else, right? Because that's what it means of optimal usage. let's see. If you have different pizza stores and you bought lots of salsa and you ship them to different places, and one of the stores there's a lot of pizza orders for it because there's a game nearby. There's a baseball game nearby. What you can do is you can then retransfer some of the salsa or some of the tomato sauce that you sent to one of the stores that is not being used to the other one, rather than ordering it all the way from the generator or from the distributor, because that's further away. And it's going to cost you more, right? Now, this helps, this acts as the basis for an intelligent, decentralized architecture. So you don't want to be having faults in the places that you're not finding, and you want different parts of your system to be intelligent, to be self-healing, to not necessarily be centralized, to be able to solve their own problems and deal with things, right? If there's a problem in a residential area and there are particular parts of the residential area that need more power, if I have bidirectional power flow, I won't need that additional power coming from a different area. That same area can serve its own needs by transferring this power if it is available somewhere else. As we mentioned with the pizza shop. Now, so you look at how your topology changes here. You have your different devices, your different decentralized devices, the decentralized systems, and now with the red, you start having communication between them, and you can track what is happening, and you can use that information in order to supply as much as is needed. And you can see that a lot of these things are connected together, and you can have communication between them in different places. Okay, you look at the power flow, and all of a sudden the red arrows here are bidirectional. Okay, so I have power being used here and I have power being used here. If this one needs more electricity, I can get it from here. Or if this one needs more electricity, I can get it either from here or from here, if the other devices are not using them now, right? So all of a sudden, the network that you have is very different, and you can do things far more efficiently. Now, you can think of these microgrids as being separate elements, and they, as we mentioned, are the building blocks. If you don't have these microgrids, you can't have smart grids. So these microgrids and the communication between them contributes to being the basic part of smart grids. And based on that, you can also have external systems, right? You can have cities that can interact this way. You can have microgrids in different areas. You can have cities of these, and then you have external systems. And what you typically want is your microgrid to be able to serve its own needs, have its own storage elements, as we mentioned. And if it needs more power, it could get it from other microgrids around it. Or if it has more power, it can provide it to other microgrids around it. And then if you need more power from external sources, you can also do that. And you have this type of network topology in different parts of the city, in different cities, and this is how you can interconnect between them. If you look at a wide area smart grid, you can think of having smart grids in different areas, and you can have different cities even across provinces and across countries even, being all interconnected, right? And the most important thing in here is the blue arrows that are bidirectional. So things are flowing in two different ways, and by having the interaction between these things are going to be far better. So the existing communication links are the red ones, and the future or fast communication links, especially with the technologies that we have now, Gigi Ethernet, things are going to be very, very fast, and you can interact between these different lines very, very fast. So let me see. Okay, so to sum up, the benefits of smart grids include the efficiency in the distribution and the energy management. You're increasing the reliability on your system. If you need more energy, you can get it somewhere else, which is nearby because of the communication and bidirectional power systems. The environmental benefits, because you can optimize your usage, you can optimize your generation by using green sources for generating electricity, and only when you need additional power that the green sources cannot provide alone, then is when you start using your fossil fuel resources or generation mechanisms. Okay, so we're going to work on this in the afternoon, the smart grid barriers. Now, I was wondering if you have any questions regarding smart grids, the different components that come into play, and maybe if you have any detailed questions about how these different things work, also feel free to ask me. Yes?
You said the one after this?
Yeah.
This one flows in both ways, right?
The power. This is not just the communication. The actual power flows in both ways.
And the one before it, this one does not?
And this is showing two different things in it. Both of these are for the intelligent power, intelligent microgrid. So it includes both of them. So the microgrid itself does not. The microgrid itself includes the distributed storage units, but so that it could handle its own system, its own area. But with the intelligent microgrid, it's when all of a sudden communication becomes a big issue. That's why you have lots of investments and lots of work in this field now. But a lot of, as you can see, a lot of the things that you have are, you need the new devices, especially if you have systems that have been existed for 40 years and they have been working. It's harder for people to understand why they need new equipment and smart meters, and dealing with different issues of, for example, privacy. People know when they're turning on their washing machine. I mean, I don't know. If you think about the fact that cable companies know what channel you're watching all the time, that's how they get the ratings, right? For every show, then turning on your washing machine is not that big of a privacy issue. But there are of course lots of issues with that, and we'll be discussing that in the afternoon. Okay, any questions about the different components of the smart grids? So can you now go to your, I don't know, parents or friends and explain power grids and what you need in different elements of it? Yes? Hopefully? Okay, thank you so much. We'll wrap up now, and we'll see you in the afternoon at 1.